Bismillah ar-Rahman ar-Rahim. Square matrices X and Y are of size m by m. Xy is equal to x squared plus y squared. We want to prove that if the matrix xy minus yx is invertible, then m is a multiple of 3. The contrapositive of this proposition is that if 3 is not a divisor of m, then xy minus yx is singular. That is to say, the determinant of xy minus yx is 0. Consider non-zero complex number beta. From the properties of matrix determinant, beta to the m times the determinant of xy minus yx, m is the size of this square matrix. This is equal to the determinant of the matrix multiplied by the scalar beta. We are given this piece of information, which means that x squared plus y squared minus xy is the all-zero matrix of size m by m. So this determinant is equal to the determinant of x squared plus y squared minus xy. These three terms are the all-zero matrix plus beta times xy minus yx. This is equal to the determinant of x squared plus y squared plus beta minus 1 xy minus beta yx. This is a quadratic polynomial. Let's try to factorize it. Consider the product of the matrices ax plus by and eta x plus gamma y. Expand. Compare with what we have here. We should have a eta equal to 1, b gamma equal to 1, a gamma equal to beta minus 1, b eta equal to minus beta. From here, a is equal to 1 over eta. From there, b is equal to 1 over gamma. So gamma over eta is equal to beta minus 1. Eta over gamma is equal to minus beta. If we multiply these two ratios, we get 1. So minus beta times beta minus 1 is equal to 1. Beta satisfies the equation. Beta squared minus beta plus 1 equal to 0. The two solutions to this equation is e to the plus or minus I pi over 3. Set beta equal to e to the I pi over 3 and eta equal to 1. From here, gamma is equal to minus 1 over beta. This is minus e to the minus I pi over 3. Minus 1 is e to the I pi. So gamma is equal to e to the I 2 pi over 3. A is equal to 1. B is equal to e to the minus I 2 pi over 3. Let's go back here. Beta to the m times the determinant of xy minus yx is equal to the determinant of the product x plus e to the minus I 2 pi over 3 times y. This is one bracket. In the other bracket, we have x plus e to the I 2 pi over 3 times y. As given in the problem statement, the elements of matrices x and y are real valued. So this matrix is the complex conjugate of that one. This determinant is equal to the magnitude squared of the determinant of x plus e to the I 2 pi over 3 y. Beta to the power m is e to the I pi m over 3. X and y are real valued matrices, so this determinant is real valued. What we have on the right-hand side is the magnitude squared of a complex number. So the right-hand side is real valued and non-negative. If m is not a multiple of 3, this exponential is complex valued. What we get on the left-hand side is a complex number with a non-zero imaginary part, but we have a non-negative real number on the right-hand side. The only possible way to be in this situation is that this determinant is equal to 0. Matrix xy minus yx is not invertible. We have proved that if small m is not divisible by 3, this matrix is not invertible. This is equivalent to this proposition here. If xy minus yx is invertible, then m is divisible by 3. In the second problem, we have a binary matrix whose components are 0 or 1. The square of matrix A is the all-1 matrix. The all-1 matrix of size m by m is denoted by omega sub m. For m greater than or equal to 2, can we have an m by m matrix with 0, 1 elements and such that the square of the matrix is the all-1 matrix? We can start the solution by investigating the product of matrix A and the all-1 matrix. If we multiply A by omega m, each column here is all-1. When we multiply a matrix by an all-1 vector, we get the sum of each row. This is the vth row of matrix A. When multiplied by the all-1 vector, we get the sum of these elements. Let's denote this sum by RV. So RV is the sum of the elements on the vth row of the matrix. Because our matrix is binary, RV is also the number of ones on the vth row. Matrix A times omega m. When A is multiplied by the first column in the all-1 matrix, we get R1, R2, all the way to Rm. We have the same output when A is multiplied by any other column in omega m. So this product will have R1 on the first row, R2 on the second row, and so forth. Another product worthy of investigation is omega m A. Consider an all-1 row vector. it is multiplied by the kth column in matrix A, A1k, A2k, all the way to AMK. This product will be the sum of the elements on the kth column. Let's denote this by CK. Because the matrix is binary, its elements are either 0 or 1, then CK is also the number of ones on the kth column. The first row in the product omega MA is C1, C2, all the way to Cm. All rows are identical to the first row. Matrix A has a special property. Its square is the all-one matrix. This product is A. The all-one matrix is A squared. This product is A cubed. Omega MA is equal to A squared times A. This is also A cubed. This means that these two matrices are exactly equal. R1 is equal to C1. R1 is equal to C2. R1 is equal to Cm. R2 is equal to C1. R2 is equal to C2, and so on. We conclude from here that each row and each column has the same number of ones. Let's denote this number of ones n. From here, we have that A omega m is equal to omega m A is equal to A cubed is equal to an m by m matrix, all elements of which are equal to n. This matrix can be written as n times the all-one matrix. The question arises as to whether there is a particular relation between n and m. Let's study omega m squared. When we multiply a row of the all-one matrix of size m by a column, we get m. Omega m squared is a matrix whose components are all equal to m. This can be written as m times the all-one matrix. We can do something else. A squared is equal to the all-one matrix. So omega m squared is equal to a to the power 4. A to the power 4 can be written as a cubed times a. A cubed is equal to small n times omega. Omega m times a is equal to n times omega m. Omega m squared, which is a to the power 4, is equal to n squared times omega m. These two matrices are equal. We have m minus n squared, that's a scalar, times the all-one matrix of size m by m. This is equal to the all-zero matrix of size m by m. The only possible way to achieve this is that m is equal to n squared. To be able to construct a binary matrix A such that its square is the all-one matrix, m must be a perfect square. Since by the problem statement m is greater than or equal to 2, then m can be equal to 4 or 9 or 16, 25, and so on. These are the sizes for which we can satisfy the requirement in the problem statement. We are not done yet because we need an explicit construction of such a matrix A. Matrix A is of size m by m. We can think of A as constructed from submatrices. Each submatrix is of size n by n, or square root m by square root m. We have n by n blocks. For matrix A to have n ones per row and per column, we need each submatrix to have 1 1 in each row and 1 1 in each column. If we choose each submatrix to be identity of size n by n, A squared will not be a matrix of ones. We cannot make each submatrix equal to the identity matrix of size n by n, but we can try to make each a slight modification of the identity matrix. Let I sub 0 be the identity matrix of size n by n. We want each row and each column to contain 1 1. What we can do is to do circular shifts. Specifically, define Ik to be the identity matrix with each row circularly shifted by k positions to the right. Let's index the rows and columns of the matrix by the set of non-negative integers 0, 1 all the way to n minus 1. In this case, the topmost row in matrix Ik will be in the kth position. If n is equal to 4, we have matrices I0, I1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, then 1, 0, 0, 0. I2, 0, 0, 1, 0, 0, 0, 0, 1, then we have 1, 0, 0, 0, 0, 1, 0, 0. Finally, we have I3, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. These are the matrices relevant to the special case of m equal to 16 and n equal to 4. What happens when we multiply two of these matrices? What is element AB in the product IKIV? Rather than using an index from 1 to n, the index takes values from this set. What is row A in matrix IK? Row A is 0, 0, 0, and then there is 1 followed by zeros. This one is in position K plus A modulo n. For instance, if n is equal to 4, K is equal to 2, and A is equal to 3, where do we have the unity element? It is in position 5 modulo 4, which is 1. This is this one here. Don't forget that we index starting from 0. Where is the unity element on the leftmost column? Here the positions are 0 and 0. Here 1 and 3. Here 2 and 2. Finally here we have 3 and 1. We can generalize this and find that the sum is n modulo n. That is 0 modulo n. So what is column B in this matrix? We have zeros, 1 and then zeros. Where is this one? The one in the leftmost column is in position n minus v. V is the position of 1 in the topmost row. Then we add b. Like here we do our computation modulo n. When we multiply the row vector with the column vector, we get 0 unless the ones are in the same position. We need k plus a to be congruent to n minus v plus b. This is done modulo n. N modulo n is 0. Moving minus b to this side. B is congruent to a plus k plus v modulo n. In matrix IK, row A has 1 in position a plus k modulo n. In the product, row A has 1 in the position a plus k plus v modulo n. In the topmost row of IK IV, the 1 is in position IK plus v. This means that this product is nothing but I of k plus v. To be specific, IK times IV is equal to IK plus v modulo n. This is for k and v in the set from 0 to n minus 1. Let's see how this result justifies the following construction of matrix A. A is of size m by m. M is a perfect square. The square root of m is n. We put here I0, the identity matrix of size n by n. All these blocks will be I0. We have n blocks. Then we have n blocks equal to I1, then I2, all the way to in minus 1. We end up with n1s per row and n1s per column. The question now is, what about A squared? When we multiply a horizontal block from here by a vertical block, we get I0, Ik, k can be 0, 1, 2, all the way to n minus 1, plus I1, Ik, plus I n minus 1 minus k Ik, plus I n minus k Ik, plus I n minus 1 Ik. According to this result, this is Ik, this is Ik plus 1, this is In minus 1, n minus k plus k is n, which is 0 modulo n, so this product is identity of size n by n, that's I0. Then we get I1. The last product is Ik minus 1, which is In minus 1 if k is equal to 0. No matter what block we choose from here or from there, we obtain the sum of these matrices. When these matrices are summed, convince yourself that you will get the all-one matrix of size n by n. And A squared will be the all-one matrix of size m by m.